All right, in this example, we'll solve for the contact time this time during the collision, given the average stopping force. NASA's Langley Research Center has been experimenting with the use of airbags to soften the landings of crew exploration vehicles, or CEV for short, like shown in the picture on the left here. What stopping time will be required in order to safely stop a 7,280 kilogram CEV moving at a speed of 6.31 meters per second with an average force of 356,720 newtons? All right, once again, our expression relating momentum change, force, and time looks the same. And in this problem, we're solving for this stopping time, or this impact time. We're given the net force already, and we need to solve for the changed momentum because that's the only thing that we don't have at this point. However, we can do that. I know that the momentum of the vehicle before the collision will be the momentum of the vehicle with the velocity that it was given to me. So I know that we're assuming that these vehicles are sort of released from some position above the Earth, and the mass of the vehicle is 7,280 kilograms, and it's essentially falling with a speed of 6.31 meters per second right before it hits the ground. Okay, so I know that the momentum of the object right before it hits the ground will be equal to roughly 46,000 units of momentum. And after the collision, right, after it hits the ground, essentially, that's essentially a collision, it should stop, right? The momentum of the vehicle after it hits the ground, we want it to be zero. We want that to come to a nice stop. And so the change in momentum in this case will be that negative 46,000 units of momentum. And again, I would encourage you to use the exact value here. So when we're solving this problem now, we can rearrange again for delta t just like we have before. Delta t will be equal to, in this case, I'll divide both sides by the net force, the average net force, right? And I can go ahead and plug my values in. That'll be negative 46,000 units of momentum over, and in this case, the force wasn't explicitly told to me that it will be negative, but I know that I have to apply the force in the opposite direction that the car was traveling in, right, to stop it. So if I said that this 6.31 was positive, well, then it should make sense that the force needed to stop it will be negative. In other words, we have to apply a force against the direction it was moving, otherwise it won't stop. And so I'll go ahead and say that's negative 356,720 newtons. And again, this is the same units for momentum we've been using so far. That'll be equal to 0.129 seconds of time needed to stop the CEV. All right, so again, very similar solving approach as the previous example problem in just identifying the variable that you don't have and then using your understanding of impulse and momentum to rearrange the expression to solve for the variable that you want. All right, let's take a look at one more example problem.